Now, dear student, chapter number 3, motion in a straight line, and today we have the topic kinematic equations of motions by the integral calculus. So it's a very simpler method, and already we have discussed the graphical method, and in which we have discussed the three equations of motion. So it is another method in front of you, that how we are just using the basic concept of the integral calculus here. Now here we have the first equation of motion, and generally the another name of the first equation of motion is the velocity time graph, dear students. Now generally we are representing it that v is equal to v naught plus at. So here v is the initial velocity, v naught is the final v is the final velocity, v naught is the initial velocity at the t is equal to 0. Now a is the acceleration and t is the given concern of the time we have. Now we have to be discuss the derivative portions. In the derivative portions, I have told whenever we are just making the first derivative of the that mean velocity with respect to time, so it will give the acceleration. Now easily we know the integral calculus is a reverse process. So how we are just operating? So as per the nature, the velocity and the time can be given by the relation that is called the acceleration, and we will talk in the sense of the that mean derivative part. Okay, but here we have to be that mean move in a reverse direction. So this is the finalized equation we have of the derivative. Okay, now how we are just operating, just see it. Now I am just putting that mean in the term of the integral, this one equation number 1. So I am just writing dv is equal to a dt. Okay, and we have to be operate this one that mean equation within the limit, because we know the basic graph which we have plotted. Okay, so this one graph is the kind of this. Okay, and we are just getting the basic concept that time limit is available from 0 second to t second. Dear students, just see it, up to 0 to t second we have the time interval, and we know the nominations in the graph o, a, b, c and d. Yesterday we have made this one, and we are just getting the intercept on the y-axis. So the final velocity, that's mean o, b, or, that is called the v. Okay, so we are just getting the two limits of the velocity. One limit is the final limit, that is called the v, and initial limit, that is called the v naught, that lies up to oa. v naught is the initial velocity. So we will discuss the two limits. That means velocity is changing from v naught to v, and time is changing from 0 to t. Okay, so we will apply the limit on the relevant integral. So here just I am applying the limit on the velocity part, that is called the v naught to v, and we have to be made the integral with respect to dv. Okay, now here we have the integral on a time. Okay, so we are just putting a outside, that is acceleration outside, and we are just putting the limit, that is 0 to t. Now here there is a no kind of the function we have in the both side. So what should we do? We have to be create the basic mathematics. That mean we will utilize the basic mathematics here, and creating a function. So I am just writing v naught, that v raised to 0, and simply its a meaning is the 1, dear students. Now a, here I am also making the simplify justification that t raised to 0 and the dt is there. Now it's a very much easy integral, that power integral, and already we have discussed, if we are just making the integral of x raised to n, so what should we do? That means dx. So whenever we are just making the integral of that part, so further I am repeating in the short. Okay, so just pay the attention. So whenever we are just making the integral, suppose the limit is there, that is 1 to 2 is there. So how we are just writing that x raised to n plus 1 is to be divided by n plus 1. So I will do this type of the integral, and with the limit 1 to 2. So here I am just doing the same thing. Okay, so it is a v naught plus 1 is to be divided by 0 plus 1, sorry. Okay, and the final limit, that mean v naught to v. Here we can also make the that mean integral on a t, because we have the relevant integral with respect to time. Okay, so I am just writing t 0 plus 1 is to be divided by 0 plus 1, and the limit integral, that is called the t. So what we have to do next, we have to be apply the that mean limit in the v. So once I am just writing v, and the next limit we have, that is called the v naught. Okay, now here just I am keeping the a outside and giving the value to the t. Okay, one is that now as I am just keeping the t at the place of the t, and then 0 at the place of the t. So we are just getting the first equation of motion. V minus v naught is equal to at, and v is equal to v naught plus 80. So dear student, it's the first result we have on behalf of the that mean integral portion. Okay, so it's a very simpler integration, need not to be afraid from this integration. Only you have to be learn the one step, that mean power integral. Okay, so we are just getting the same result as we are just putting here. Okay, now second equation of motion. Now dear students, here we have the second relation, that is called the second equation of motion, and sometime it is known as a position time relation, and sometime it is called the displacement time relation. So these are the relevant version, those are given in the NCERT book. X minus x naught, x is the position at the time t, x naught is the position at the time t is equal to 0 from the origin. So we are just representing in the term of the displacement. Okay, so this one equation we can use here, that is called the position time relation we have. Now here we are just representing the equation in the another manner. Whenever we have the initial positions at the particular t is equal to 0, dear students, now we are just using as is equal to v naught t plus half a t square. So it is very much familiar result to you up to level of the 9th class. So in the 9th class we were writing that as is equal to ut plus half a t square. So it is a very simplest part we have. Now it is called the displacement time relation. So how we are just getting, so here we have the two word, that mean position and the time, or you are using the displacement and time. So pay attention that between the displacement and time, which quantity gives us the relation. So I am just writing that f, as I am just making the first derivative of the displacement. Okay, so I am just getting the notification, okay, of velocity. So the velocity is a quantity which gives the relation between the displacement and time. So easily we can operate the integral on it. Okay, now v dt, okay, that is equal to the ds. Clear? So this is the changing of the equation we have. Now we will put the meaning of the that mean here v, and applying the proper unit. Okay, so here I am just applying the unit because time interval on behalf of the graphical notation, that is called the 0 to t, and we have to be operate the integral with respect of the time. Okay, now here we have the integral with respect to that mean displacement. So initially the displacement is a 0, and we have the final displacement, suppose we have, that is the s. Okay, now what we are doing, we are using the equation, that means v is equal to v naught plus et in the equation number 1. Okay, so how the integral that comes in front of you. So I am just writing 0 to t, and at the place of the v I am just writing, that means v naught plus at, and with respect to of the integral, that is called the dt, and I am just putting the 0 to s and the ds. So it's a modification of this equation. So how we are just operating, so we are using the basic integral rule. We should apply the integral on a each part. Okay, and quantities, those are not relevant, keep outside. So here we have that v naught dt plus integral of that 0 to t at dt. Okay, it's a representation, and that 0 to s and the ds. So it's a, that mean representation of the equation number 4. Now quantities, those are not relevant for the integral. So in general word I am just saying that these are the that mean not that mean appropriate. Okay, so keep them outside, and we have to be operate the integral with respect to time. Okay, here the acceleration is not relevant to the integral, that mean, and we have the integral, that is 0 to t and t dt, that is equal to, and here we are just although approaching that the 0 to s and ds. Here we don't have the function, so we are just creating s raised to 0, and simply the meaning of this is a 1, so it doesn't create the impact in the term of the magnitude. Here we are just also changing the integral, that we don't have the any kind of the variable. So here just I am changing it in that part of the that t raised to 0. Okay, now it's easier to operate the integral of x raised to n. Okay, so here just I am starting that v naught, and integral of that t 0 plus 1 is to be divided by 0 plus 1, dear students, and with the limit of 0 to t. It's the first integral portion a, and we are just increasing the power of that t raised to 1. Already is given 1 plus 1 is to be divided by 1 plus 1. Okay, with the final limit section that is called the 0 to t. Okay, and here we have also the same thing as 0 plus 1 is to be divided by 0 plus 1, dear students, and with the concern of the power, that means 0 to s. Okay, this is the part of the displacement we have. Now what actually we are using, that we should apply the limit, that as we are just giving the limit t to t, so we are just getting t, and then we are just applying the 0, that is called the t minus 0. Here we have a by 2, we are just keeping the 2 in the denominator and keeping outside, so here we are just also getting the t square. Okay, 0. Okay, that is equal to, now this is the s. Okay, now this is the I think we are just getting the shape of this equation, so I am just writing this equation in the systematic manner. So easily I can write that s is equal to v naught t plus half at square. So dear students, it's a second equation of motion. Somehow we want to make the change of the s by the relevant, that means things x minus x minus x naught. So it's another representation of this equation. Okay, so this is the second equation of motion, and these are the very much easier part we have. Okay, now third equation of motion we will discuss here. Now dear student, third equation of motion. Now another name of this equation, that is velocity position relation, velocity displacement relation. This is the velocity position relation we have. Okay, and this is the velocity displacement relation we have. As we are just representing the x minus x naught is equal to simply by the s. So it makes the concern of the displacement we have. Okay, so how we are just getting the relation, this one. So I am just starting this. Now here we know the acceleration is equal to dy by dt of v. So we are just finding the respective relation in the term of the velocity. So what actually I am doing, I am just doing with the small portion of that displacement, ds upon ds. Okay, so this is the first change which I have taken here. Now I am just making the group of these. Okay, now we know the dy by, that means dt and ds, it is a kind of the group we have, and this one is the first derivative of the displacement, that this one ds and this one dt I have matched up here. Okay, and next portion, that is called the dv, and is to be divided by ds. Okay, now I am just cross multiplying the a and the ds here, so we will get the relevant equation that makes the proper relation of the third equation of motion. So I am just writing a ds, and easily we know the first derivative of the displacement is called the velocity. So we are just writing at the place of the ds, dy by dt of s is the v, and here just we are just writing that is dv. So here it is a very much relevant equation which gives the that mean relation between the velocity, position and acceleration. So now it's a conversion of this equation. This is the first equation we have. Now what is the next segment we have? We have to be apply the relevant limit. Okay, here we can that apply the 0 to s, and here we have to be make the integral in the reference of the velocity. So we are just applying the v naught to v. These are the this is the lower limit, and this is the upper limit. Okay, final limit. Okay, so always the quantity which having the less magnitude, or the initial part which playing the role, so we are just keeping in the lower part. Okay, here also the displacement at the t is equal to 0 is the very less, so we are just keeping here, and then the final displacement we have. Now I am just operating this one integral. So how just I am doing this one, a integral. Now the relevant function is there, relevant function is not there, so we are just creating as to ds, as not to ds, and with the limit of 0 to s. Here we are just already we have the function that is called the v naught to, that means limit, and the function is the v, and we have to be applied the integral, that is dv. So how we are just approaching it, a as 0 plus 1 is to be divided by 0 plus 1, and with the limit of 0 to s. Okay, now just I am applying the integral on the v raised to 1. V raised to 1 plus 1, student here 1 plus 1, and with the proper limit, that means v naught to v. So this is the representation of that portion we have. Okay, now what actually we are doing now, a and the proper that mean placement of the units we have as minus 0, this that, and 1 upon 2, and what actually we are getting, v2 v square minus v naught square. So this is the shape of the equation that we are getting. Now I am submitting in a systematic manner. So v square minus v naught square, that is equal to 2as, and it is the third equation of motion, and somehow you can also write in the term of that v square v naught square, that mean plus 2as. Okay, so this is the that mean relevant equation, either what actually you are using, v square minus u square. So in the ninth class what we are writing, that v square minus u square is equal to 2as. So these are the similar parts we have, or either you are just representing in the term of the position. So how can you write that v square is equal to v naught square plus 2ax minus x naught. Okay, this is the representation of the another representation of the that mean equation in the another manner. So here we have the three equations of motion by the by the integral calculus. So already I have discussed that whenever we are just making the derivative of the displacement, so we will get the displacement, we are getting the velocity. So dear students, whenever we are just getting the first derivative of the displacement, so actually we are just getting the velocity, and as we are just getting the first derivative of the velocity, so we are just getting the acceleration. So for the integral method we have to be turn out in the reverse direction. So what actually I am using, v dt is equal to ds, and in this case we have to be apply the integral further. So by this method we will get the displacement. Okay, now here we just applying the that mean integration, that mean a dt, that is equal to dv. So here further we are just getting this one kind of the scene, and we will get the finalized velocity, because acceleration having its own unit on behalf of the unit system. If you are just merging it, meter per second square, when, and this one is a second, so second to second cancel, so finalized answer will be available in the part of the velocity, and here we are just getting the same thing, that is called the meter per second. So here we are also assessing it by the concept of the unit. So we have the meter per second, and I am just cancelling that mean with time to time. So whenever we are just moving in a reverse direction, so we are just getting the new quantities. Okay, so this is the derivatives, those are available in the physics, and we are just operating in a different direction. So we are just getting the final result, that is one is the displacement and one is the velocity. So this is the utility of this segment. Now students, this one portion that which I have completed. Okay, and stick to the revised syllabus that is prescribed by the CBC. If anyone don't have this kind of the syllabus, so you can contact to me, and by tomorrow we will start the revision. Okay, thank you, have a nice day, and be safe, stay at the home.